Good morning, lovely 13s. Right, buddies, we are continuing to rock on in our amazing dynamics unit. You guys have shown that you're pro at figuring out forces when something's been on an inclined plane. You know about the normal contact force, you know about weights, you know about applied forces, you know that the overall force, F net, is equal to ma, and that the other forces are not. And so pretty much you're in a state now where we can start taking it to the next level. How exciting! Okie dokie. And so for today's lesson, I'm going to put the title Friction, which sounds like something that might just be a bit boring, but actually I think the friction stuff is actually a bit fascinating. So yeah, friction. You guys already know what friction is, just in terms of real life. Essentially, if something has got a lot of friction, it's difficult to move. So if I was going to try to push a bookshelf, for instance, along carpet, that'd be very hard to push the bookshelf along carpet because there's a great deal of friction between carpet and a bookshelf. If I was going to try to put Velcro on the bottom of a bookshelf and put the other type of Velcro on the floor and push that, well, that would be like an impossible amount of friction, a huge amount of friction that would generate. And yeah, that's what friction is. If you have something that's low friction, that might be something like a curling stone or something. I'm showing I'm Canadian apparently, but yeah, like a curling stone along a curling rink, because ice is very low friction, and a stone is very low friction too, because they're both smooth. It would slide along. So that'd be an example of low friction. And that's also why your cars slip, and why in the UK cars slip all over the place in the winter, because you guys use regular tires all year long, whereas in Canada and in the northern states we have to change our tires out every year because we have to drive in snow all the time, and tires in snow are too slippy, so we have special tires. How exciting. Oh my gosh, I'm going off on a rampage. Anyway, in case you're interested, because I am, here's a little picture that I found online that I wanted to tell you. It tells you why friction actually works. So as much as surfaces, like hard old surfaces like this box and this floor, or just any surfaces you can imagine in real life, like your calculator and the desk, as much as they look like they're smooth, no surface is actually smooth. So if you were to zoom in really close on the bottom of this box and the floor that it's on, it would actually look really, really jaggy like this. And this is actually where friction comes from. It would look jaggy like this, and that means in order for it to move, it actually wouldn't be just slipping along. It would be like breaking off those little microscopic pieces as it slides along, and that takes a good deal of energy to do, and that's why friction slows stuff down. So that's kind of what's happening. If you want to zoom in even more, oh my gosh, you got me on a tangent now. If I zoomed in even more on this picture, actually at an atomic level, they kind of sink into, this is almost like chemistry even, they almost kind of, like the atoms will want to position themselves so that they're in equilibrium, and it's actually the electrostatic force, so it's like the force of repulsion and attraction between the actual charges of the atoms that make them want to be in a position. And so in order to move, as soon as you start pushing on them, they're like, nope, 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 don't like it, until finally they give, and they're like, oh, okay, and then they slip along a little bit, but they still fight the whole time. So yeah, friction sounds boring. It's quite interesting though. I think it's cool. Okay, but anyway, here's what we got. It's a formula, okay? Now the force of friction, it's just got different letters depending on the textbook. So FF is what I call it, force of friction, and it's mu R. Now mu, my buddies, is mu is called the coefficient of friction, okay? So I'm going to write that down. Coefficient of friction. And you guys already know what R is. R is the normal contact force. Normal contact force. And it's R, contact force, and it's R because it's a reaction force. Okay? So that's a normal contact force. Now it's based on those two things, which of course it would be, because it's a property of how sticky surfaces are, so it better be linked to the surface, and R is the only force that's really linked to the surface when we're doing our questions. Yeah, so that's it. Essentially, mu can be any value, so, or well, yeah, mu can, no, it can't be a negative value, but yeah, mu can be most values that are bigger than 0. If mu is 0, there'd be no friction at all. That doesn't exist in real life, but you can get close to it. That'd be something super slippy. So the curling stone on the ice would be a low mu, but certainly not 0, because it would stop. If mu was, say, for instance, anywhere in between 0 and 1, that's kind of what you normally get. So more sticky is toward kind of 1 and less sticky is toward 0. If mu equaled 1, it would mean that the force that you'd have to push on an object with to make it move would be the same force that you'd have to lift it up with. So if ever you had a mu bigger than 1, you'd be better off just lifting the thing up. So, for instance, say I had a bookshelf, but I brought it to the beach for an inexplicable reason. If I was going to move a bookshelf along the beach, I wouldn't push it through the sand, because the sand would pile up in front of it and make it impossible for me to move. But rather, I would just lift it, because that's the only way you'd be able to make it move. So, hooray! Big, long spiel about what friction is. Cool. Now, this here, F-lim, they call that limiting friction. It's just another way of saying friction. They usually use this one specifically when friction is about to break. And F-max they use as well. This is what your textbook actually uses, is F-max. They call the friction F-max because friction can gain up to a certain amount of force, so it can be a certain number of newtons, and past that point it just kind of sticks at that level, and that's why they call it. So for instance, maybe there was like 20 newtons of friction, well, and then you pushed it harder than 20 newtons, it can't actually make more friction than that, so it stays at 20 newtons, and that's why they call it F-max. But I call it FF because I think that's just all, I don't know, making it complicated for no reason. FF is force of friction, and it's mu r. Cool beans. So, here we go. The most important thing of all. And friction opposes motion, which I think, of course, it would do. So if something was sliding along, it's going to stop it sliding along. But it also opposes intended motion. So if ever you've had to, like, push a car, and the car doesn't move, it's because the friction, you've not overcome the friction in the car. And so even though it's not moving, that is still friction, okay? If you're pushing against something but it doesn't go, it's because the friction is opposing your force at equaling the same amount of force that you're putting in, so you can't make it move. So, how exciting. Okay, first question. A particle of mass 5 kilograms is pulled, oops, I don't need the word pulled. Okay, 5 kilograms is pulled along a rough horizontal surface. Okay, that key word there, rough, means that we're dealing with friction, by horizontal force of magnitude 20 newtons. The coefficient of friction between the particle and the floor is 0.2, which means that it's not very slippy. It's pretty slippy. It's kind of, yeah, slippy-ish, but not super slippy. That's how exciting. Find the magnitude of the frictional force. Okay, buddies, guess what? Because remember how I'm making you do all these same steps in every single question? This question, even though it's a friction question, is exactly the same as all the others. So what do you always have to do first? What's step 1? That's right, buddies, a free body diagram. So let's do it. It says it's horizontal, so draw horizontal. Bang. It says it's a particle. Draw a particle. I'm drawing a box because I always draw a box. That's 5 kilograms. Cool, free body diagram. What is there on the, what forces are acting upon it? Well, to begin with, there's certainly a weight because we are on Earth here and there is a weight pulling it down. It's on a surface. There's definitely going to be a reaction force as well, otherwise it would fly through the surface. And it says that it's being pulled along by a horizontal force. I'm just going to go with it's being pulled along right by a horizontal force. I'm going to call the force F, and the force is equal to 20 newtons. It says that the mu is 0.2, and is it accelerating? Horizontal force, what's that? Oh yeah, sorry, that's part B. It is accelerating. It's going to be, if it's accelerating, it's going to accelerate this way, okay? Because that's the way it's being pulled. And here you go. You ready for your new force? Boom, friction. Because you're pulling it to the right, we're going to call it FF. Like we could call it F-max, like the book. I'm just going to call it FF, though. And it doesn't have to be red. It can be the same color. It's no different to a normal force. And yeah, it's opposing the intended motion. We're pulling it to the right. Friction's going to go left. Cool beans? Cool. Now, here we go. Question 1. It says, find the magnitude of the frictional force. It bothers me when questions are written like this because it's kind of adding an extra step that we don't have to really worry about. But anyway, you shouldn't number plug, but in this first instance, I think it's kind of forced us because it's just said what is the magnitude of the frictional force. So here we go. Unfortunately, we have to do it this way. It's a number plug, so I can't do horizontal and vertical like normal, so I'm going to have to do a number plug. I wish that there's only part B and not part A. If there was only part B, we could cut to the chase. That'd be better. But Anyway, let's do the magnitude of the vertical. So I don't like this. Makes me sad, that one. So here we go. We have to number plug, unfortunately. So force of friction is mu r. Okay? So we already know what mu is. So that's a great big tick. Mu is not 0.2, but we don't know what r is. So we need to get r. Okay. Now, at least, though, buddies, we get to do my method now. Okay? We get to do the method from last time. So you say to yourself, where's r? Horizontal or vertical? That's right, vertical. So what you write is this. You write vert. You define a direction to be positive, up or down. It makes no difference. And then you write down your F net equation. F net, the overall balance of forces, is going to equal everything up, which is R, and that's all the forces that are up. Take away anything down, which is W. Is it accelerating? Is it accelerating vertically? Will it leave the surface? Well, no. So F net is 0 because F net is MA, and A is 0. Which means that 0 equals R, take away W, which is mg, which is 5 times 9.8. Cool? Which means that R, bish bash bosh it into your calculator, is 5 times 9.8, which is 49. So R is 49 newtons. Cool? Which is sweet. Now that's a normal way of doing it. Now unfortunately, now we got to go to our stupid number plug, and here we go. We can get the force of friction then. Which means that the force of friction is going to be mu, which is 0.2, I think it was 0.2, 0.2, and r, which is 49, which means that the force of friction in this question is 0.2 times 49, oops, I typed 0.5, 0.2 times 49 equals 9.8. So there's a resisting force of 9.8 newtons, and that answers the first question. And actually, this then is 9.8 newtons. Cool? Now, usually they wouldn't actually ask for the force of friction on its own as a force. Normally what they do is they'd say, oh, what's this acceleration, like they did in B, and not help you with A. But they're trying to help, but I think it makes it harder when they help. Cool. But now we can do B. B's fun. Okay. In B, it says, find the acceleration of the particle. So we're after the acceleration now. Yeah, and that's wicked. Now we can do our normal way. So which way is acceleration, horizontal or vertical? That's right, horizontal. So what do you write? Hor, just like that. Define a direction to be positive, to the right. And here's what you're going to write down. And I picked right because that's the way acceleration is. That's sensible. Cool. And you get this. You're going to get F net equaling, so the overall balance of forces equals anything to the right, which is the 20 newtons, so 20. Take away anything to the left, which was the force of friction. Now, I could just put 9.8 in, and I will, but this is how a normal question would be, that it wouldn't have actually told you to figure it out in the first step, and you just put mu r in there. But we have actually done that, so let's cut to the chase. F net does equal ma, so ma, because it is accelerating, is going to equal 20, take away 9.8, which means that we know what m is actually as well. M is 5, so we're going to get this. We're going to get 5a equals 20 take 9.8, 20 take 9.8, and bish bash bosh that in your calculator, and you'll have it, my lovelies. So 20 take 9.8 divided by 5 equals 2.04. So the acceleration here, my lovelies, 2.04 meters per second squared, like a boss. So we introduced friction, which is a lovely, exciting thing, and this is what we've wound up with. It's quite good. It's no problem. We just have done a question there. Cool. We're going to go one step harder on now on the next question. So here we go. Right, a little bit funnier this one. So this is just another example of where they kind of make it just a bit wonky on purpose. They're just trying to drive that formula home. The force of friction is equal to mu r. They're just trying to drive that home. So they've made a little unusual question. So a block of 5 kilograms lies on a rough horizontal ground. The coefficient of friction between the block and the ground is 0.4. A horizontal force of P is applied to the block. Find the magnitude of the frictional force acting on the block and the acceleration of the block when the magnitude is blah, blah, and blah. Right, buddies. So every single question that you do here needs the same first step. And what's that first step again? That's right, a free body diagram, buddies. So let's do a lovely free body diagram. So here we go. There's our block. on the rough horizontal ground there. It weighs 5 kilograms, 5 kg. And what forces is acting on it? Well, yeah, it's got a weight because it is on Earth. It's got a normal contact force, a reaction force of R. It's going to have a horizontal force of P, it says, and it's just going to change P, but I'm only going to draw this picture once. I won't actually write what P is. And then, of course, there is friction, which opposes motion or intended motion. So even if P doesn't actually make it go, there's still a force of friction that way that has prevented it from going. Cool. If there's an acceleration, it will be that way. Cool beans. Right. So for part A of the question, actually I'm going to erase the A and write it over here. So for part A of the question, it's like, what do you do if, what would be the frictional force if P was 10? Well, here's we go, my buddies. Unfortunately, we can't just do this normal with an F net equation, and it's because it's a question just specifically about the frictional force, which is actually very unusual, but that's how they've decided to do it, so that's what we'll have to do. So here we go. We know in general, and you don't usually number chug like this, I'll show you in the next question, but we know force of friction is equal to mu r. Now that is always true. So now have a look at what you've got, and it does say that mu is not 0.4. So we do know that, but we don't know r. Cool beans? So we need to get r first. So if we're going to get r, buddies, how are we going to get r? Well, now we get to do it the normal way. We're going to have to consider a direction. What way does r point? Up! So which direction should we consider? Vert! That's right, vertical. Pick a direction to be positive. I'm going to go with up, and here we go. F net, the overall balance of forces, equals r, take away w. Now, there's no acceleration vertically because it doesn't fly off the surface upward, for sure. So F net is ma, but a is 0. So F net is 0. So 0 equals r, take w. W is mg, though. So 5 times 9.8. Cool beans? Which means r is equal to 5 times 9.8. 9.8, 4.9 is it by any chance? 49, yeah, exactly, good. 49 newtons. Cool. So the normal contact force is that. Which means for part A then, the force of friction that you could get would be this. It would be not 0.4 because that was the coefficient of friction, times by 49. So let's do it. The force of friction that you could have got was 0.4 times 49 equals 19.6 newtons. Okay. Now, here we go. This is what I mean about this is just a bit of a trick question, and it's weird, and they won't usually ask a question like this on the exam, but it's saying that the force of friction is 19.6 newtons. That would mean, if you look at my cursor, that you have 10 newtons pulling to the right and 19 newtons pulling to the left. So if you had 19 newtons pulling to the left, in which way would this thing actually accelerate? Well, yeah, if you said it would accelerate to the left, that's right. So if the force of friction was actually 19.6 newtons, it would accelerate to the left. But obviously that can't happen, right? Because that's more than the force that's been applied, okay? This, my lovelies, is actually why the book uses, instead of FF, this is why they use Fmax. This is the maximum amount of friction that you can actually get, okay? That's why the book uses it, and it is weird. I know it is weird, but 19.6 newtons, it's not going to have 19.6 newtons. So what will friction actually be? Well, it's going to be this. So, actually, force of friction is going to only equal 10 newtons. And the reason why it's going to only equal 10 newtons is because that is the force that's required to balance out the pushing force, to balance out P. Do you get me, my buddies? So while the maximum you could possibly get is 19.6, we don't actually need that much. So we won't get the full 19.6, we'll only get 10, because 10 is sufficient to make it not move. So it is a trick question, I have to say. It's one of those weird, wonky trick questions, but at the same time, though, it's quite unusual, and it's a good question in that it does try to get you to understand how friction actually works. So it is good, even though it's unusual. Cool, so force of friction in this one's only 10 because that prevents movement. Okay, so for part B, we've got now that the pushing force is equal to 19.6. So this time in this question, this is 19.6. And actually, in this case, we still have the same maximum friction. Remember how the force of friction could, at the very, very most, be 19.6. Well, if you're pushing with 19.6 and the force of friction can take a value of up to 19.6, it's going to take as much value as it can get. So this is going to be 19.6 newtons as well. So because the force of friction can take any value up to 19.6, if you push with 19.6, you've actually reached the spot where it's going to be balanced. So here's what you've got. This time the force of friction is just going to equal 19.6 because that's its max value. That's the value it's going to take. Now if that's the case, you've got as much force pushing forward as pushing backward, which means it's not going to accelerate. A equals 0 meters per second squared. Now, they call this, my lovelies, this is the case of when you've seen, last year, when you've seen F lim. This is called limiting equilibrium because now you're at the point where the thing is about to turn, and this is like, if you pushed any harder, it would go, essentially. So we're at the point of it breaking its equilibrium. Cool beans? So just more kind of technical stuff with friction. And finally, for part C, which I will treat ourselves, and let's go in purple to do. For part C, it says that now we're going to push with 30 newtons. Okay, if we're pushing with 30 newtons, it's going to be all of the friction available resisting us. So it's still going to be 19.6 resisting us, but we've got 30 forward. So for sure, we can answer the first part of the question. What is the frictional force? Well, it's going to take its maximum value of 19.6 still. Okay, because that was the maximum that it has, and so if you're pushing with 30, you're pushing with more than 19.6. It's going to take the full 19.6. The second part of the question is to find the acceleration. So now we get to go normal again. So here we go. For horizontal, pick a direction to be positive. I'm going to pick right because that's the direction of acceleration, and then the balance of forces F net equals 30. Take 19.6. It is accelerating this time, so we're going to switch F net out for MA, but M is 5, so it's going to be 5, and A is what we want. So that's going to be 30, take 19.6, and you finally get then that the answer for this one is 30, take 19.6 equals, divided by 5 equals 2.08. So 2.08 meters per second squared. Bish, bash, bosh. And that is an example of a question that's trying to teach you how friction works, okay? That was trying to show you what happens if you don't push, you push less than the potential friction, well, then you get 10, you get it balanced. If you push equal to the potential friction, you do just get the potential friction to be equal to how hard you pushed, okay? It made no acceleration because it's limiting equilibrium. If you push harder than it, it takes its max value of 19.6. If I pushed 100, it would still be 19.6, which means you calculate an acceleration, 2.08 in this case. Cool. Now here you go. This is a real one, okay? Standard tricky one. These are like exam, and they're actually a lot better anyway. So here we go. Particle of mass 2 kilograms is sliding, get my highlighter out, 2 kilograms is sliding down a rough, so with friction, horizontal slope that is inclined at 30 degrees. Given that the acceleration of the particle is 1 and the coefficient of friction is mu between the particle and the slope. Oh, sorry, it says find that it's mu. Find the coefficient of friction mu between the particle and the slope. Cool. This is a good question, a standard question, one that'll be like what's on your exam. So what do we do in every single mechanics question? Yeah, that's it. Free body diagram. Always, always, never ever try these without. So here we go. Free body diagram. It's on a wedge there. So there we go. It's sitting there like this. It weighed 2 kilograms, 2 kg. And let's get some stuff on. So it's on a rough horizontal slope. Is it accelerating? Okay, and it's sliding down the slope, it looks like. Sliding down, you have to say down. Sliding down the rough slope that's inclined to 30. Cool. What's it experience? Well, a weight, because it's on Earth. Weight vertically downward. What else does it experience? A normal contact force, which is out this way. It's actually called normal because normal means perpendicular actually in maths, and so it's perpendicular to the surface that it's on. So it acts perpendicularly to the slopes. That's why it's out that way. That's also why it's called normal. Normal means perpendicular in maths. That's cool. There's another force acting on it as well, and that's friction. Friction opposes motion or intended motion, so it's going down the slope, so force of friction is going to go up the slope. Cool. It's also got an acceleration, given that that's 1 and it's in the direction of down the slope. Cool? Cool. Right, my buddies. Well, oh, and we're also given that this is 30 degrees. Okay. It's a hilly one, my buddies. So because it's a hilly one, we're going to introduce a new coordinate system so that we match up with the acceleration. So when you match up with acceleration, here's what you've got. I'm going to introduce x, y coordinates. X can be down the slope, y can be off the slope, up and off the slope. Which means r and ff, r is in the y direction, ff is in the x direction, w is in vertical, which isn't x or y, so this one needs to split up. So it's matching with the coordinate system. So here's what we got. This is going to be wy, and that's going to be wx, and because you've drawn it the same as me with r opposite to y to start with, that's 30 degrees. Cool? Okay. Now we're after ff, okay? That's what we're after mu, which is a part of the force of friction, which means the direction that we're going to consider is going to be the x direction. So you write down x-dir. Now here you go. F net equals, and down the slope, which is the force that's down the slope? Well, wx, you got that right. And what's up the slope? Well, ff. Cool. Is it accelerating? Yep. So we'll switch F net out for MA. And WX, I'm going to switch that one out for, W is going to be mg to start with. And WX is actually opposite, whereas W is a hypotenuse. It's mg sine 30. Now FF I'm also going to switch out for mu r. What we've just done here is what's called inline substitution, and you're always going to want to do it that way. If you do inline substitution, you'll never get it wrong, and it's really tidy and nice. So let's pop some numbers in and see what happens. So it's 2 kilograms, so what we're going to be getting here is it's going to be 2 times 1, because that's the acceleration. It's going to be 2 times 9.8 sine 30. Take away mu, which is what we want, so that's good that we don't know that. But oh no, we don't know r. So if we go through and analyze where we are, this is all just numbers, so that's all good. We want mu in the equation, because that's good, because mu is what we're after. But we don't want r. R has ruined us. Drat, if only there was something we could do to figure out what r was. If only there was a way, if only there was like a direction of travel. That's right, lovelies, we have a different direction to look at. We can do the y direction. Now if you go in the y direction, the same deal again, F net equals, and what's off the plane? Well, just r. What is into the plane? Well, wy. Is it accelerating off the plane? No, it is going to stay on that hill the whole time. It's going to stay on the hill, so there's no acceleration off the hill. So F net's actually 0 in this case, which means 0 equals r, take away, and wy is mg, so it's going to be, oops, I just got an error. I hope that that doesn't work. Okay, let's keep trying anyway. I got an error on OBS, oh no. Okay, this is a 2, and this is a 9.8, because that's going to be mg, and this time it's cos of 30, which means, my buddies, that r is equal to 2 times 9.8 times cos of 30, which means r is 17.0 to 3 significant figures. Cool? Now we know what r is. Now we're ready to go in for the kill. Bish bash bosh that in there. So you're just going to be left with 2 equals 2 times 9.8 sine 30. Sine 30. It's going to be 9.8, isn't it? Yep. 9.8. Take away mu, which is what we want, but this time r is 17.0. Cool. Work it out then. 9.8 take 2 is equal to that. Divided by 17 is mu equals 0.46. Mu equals 0.46. And mu is without a unit. This is essentially saying that it's a pretty sticky surface. It's like a Midland sticky surface, this one here. So it's kind of like normal, what you'd expect, and that's the answer. Bish bash bosh. The best way of doing it is in the x direction and the y direction and combining those using what's called inline substitution. When I look at your work, I want to see it exactly the same as my work, because this is going to make it paying dividends for you in the future. I promise. You'll need this even at university, okay? So I'm approaching this like a physicist would and like a university would. So if you can show your works like that, that's the way forward. Cool. Okay, last thing is here's what your work is for today. Page 104, question 2 to 8. And just do a mix, okay? So you don't have to do every single question, but attempt to get on some hard ones. Next lesson, I'm not going to make you a video. I'm just going to put you on live lesson so that you can practice, and I'll pick a bunch of questions for you for next lesson. So I want you to finish out this lesson, because I know it's been a long video. Finish out this lesson doing as many of these as you possibly can, getting stuck, and having a question ready for me for next time. And then next time, I'll give you just a whole bunch of exam-y ones to try. Cool? So that's it from me, my buddies. It's a tricky topic, but I think you can do it. Very, very good work. And that's it from me. Bye, buddies!